Vulkan Architecture Positive. So this is going to be a look at how Vulkan maps PowerVR GPUs and why it's a really great fit. So I will get started. As per usual, I'm Tobias. I'm hoping at least a few of you will be bored of this slide by now. Well, I'm not hoping you're bored, but I imagine you will be. I've been in dev tech for 4 years and now I'm working on Vulkan extensions. I've been working on it for the whole time. Yeah, you get the idea. So this series, this is the last one. We're finally here. Again, no new information about the API. This is just going to be adding in context to the information already done at SIGGRAPH. And this week I'll be looking at, well, as I said, how Vulkan maps to PowerVR GPUs. But first, before I do that, I will quickly, well, I say quickly, I will take a look at OpenGL and why there's a problem. So, and before I carry on, if anyone wants to ask any questions at any point, I will periodically check the Q&A app. Obviously, if you want to just save them to the end, that's fine. I may get to your question anyway, so it's up to you when you ask it, but I will try to answer it if I do see it. So OpenGL is over 23 years old now, which is a ridiculous amount of time for an API to have existed. It's not really, it's quite normal, but it's a long legacy, and hardware has moved on. The state mapping OpenGL, for instance, doesn't really map very well to hardware anymore. There's a lot of functions in there. They all look fairly cheap, and there's no real indication of that cost. It's not to say that that's necessarily a bad thing, but it doesn't express very well the underlying state machine, or lack thereof in some cases. Modern hardware is actually very complex, and there's certain bits of state, like swapping frame buffers, for instance, that can actually cause pipeline bubbles. Well, not actually cause pipeline bubbles, but sorry, let me try that again. Certain bits will cause pipeline bubbles. The example I gave will not. That will just cause a larger flush than you may have intended on certain hardware. And some state isn't even really state. It might be expressed as shader code. I think every GPU architecture has something like this, and it will require patching into the shader after compilation. If you look at my high efficiency on mobile talk, or the blog post I've linked there, there's a bit more detail on that. And I'll also talk a bit more about that later on in the presentation. Another problem, which I actually identified in the last blog post as well, and webinar as well, is implicit synchronization. So a lot of the operations in OpenGL assume that they're going to be synchronized with each other, and it's excessively so. So there's a lot of stuff that architectures nowadays can do quite cleverly. Like you might be able to run stuff in parallel that isn't obvious from OpenGL's API that they could be, or that they should be. And even though they have no dependencies on each other, they may be forced to be serialized anyway. So in place of that, drivers have to try their hardest to detect patterns of usage that can be expressed in a different way. So there's heuristics all over everyone's driver, or most people's drivers, trying to figure out what the app is actually trying to do and try and do it in the most optimal way. And meanwhile, applications have to sort of try and guess how to trigger these heuristics. So there's a bit of a back and forth, and then eventually these things get encoded in performance recommendations, which is a bit strange when there's a perfectly good API there. So one other thing that OpenGL does is it treats everything as immediate mode, and the idea is that all the commands execute in order through the pipeline. And a draw call is sort of the unit of work. So there's a small diagram that I've shamelessly stolen from our hardware discussions, which sort of details a traditional immediate mode rasterizer's pipeline. And it starts with vertex processing, goes through rasterization and shading, and ends up being written to the frame buffer. And OpenGL sort of has a model where that whole thing is executed every time you draw a draw call. Now, it might be that underlying, even in a mode like that, you've still got some overlap. It's pipelined after all, but OpenGL doesn't really assume any differences from that. And that map's okay to immediate mode rasterizers, it's sort of in the name, although modern hardware is more complex than that. And even in IMRs, there's some amount of drift from what OpenGL says it does to what the actual architecture does. And for tile-based architectures, it doesn't really fit that model. Tile-based architectures have really gotten away with the fact that actually there's a lot of leeway in the OpenGL spec. You can make it bend to your will, if you will. The actual unit of work for a tile-based architecture really is a render pass, sort of. And I say sort of because there's actually 2 stages of rendering. So here again, shamelessly stolen from our hardware discussions, presentations, etc., is a diagram of how roughly a tile-based deferred architecture like ours works. So there's 2 stages of rendering. There's a tiling phase, which does all the geometry shading, finds out the positions, and then sorts them into lists of data that goes per tile. So you split the screen into tiles and basically bin data into each of those. And then when you come to actually drawing stuff on the screen, this is the second phase. You rasterize a tile at a time until it gets to the frame buffer. And the advantage of doing that, if you're not familiar with tile-based architectures, is that it means that a single tile or a set thereof can be kept completely on chip. So if you're doing things like alpha blending or depth testing, stencil testing, all of that can be done to and from on-chip buffers without going to the frame buffer until the end of that tile, so until that thing is finally finished. And that avoids a lot of bandwidth back and forth between the main frame buffer images, which is very useful on mobile. If you actually want more information on it, there is information on our blog, and I think there might even be a webinar or not. I would have to double check that. There's also presentation material on our website if you go to the PowerVR community pages. But the main thing to note here is that after the tiling phase, the idea of a draw call is mostly meaningless. Your unit of work by the time you get to rasterization is a tile, and a tile does some work for some number of draw calls. Any draw call that touch that tile, that work will be operated on at this point. And if you happen to want to flush in the middle of a set of draw calls for whatever reason, it means you actually have to split the render up. So if you were to do draw, 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 GL flush, draw, 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 because GL assumes that you're going to be preserving the data, it makes no, it basically assumes that the data has already been written to those textures, to the textures that make up your frame buffer. And because it makes that assumption, it leads to the fact that we have to preserve that data. So we end up having to store all the tile data, every single attachment that you've used, out to main memory, do the flush, and then start the whole process of tiling and binning again, and then reload all of that stored data back onto the tile, and then continue rendering. And that whole loading and storing and restarting the pipeline is quite expensive. And in a lot of cases, when people need to actually start and stop tiling, they don't need all that data. And we have methods in OpenGL of expressing this, but they aren't particularly obvious, especially to someone who hasn't actually seen a tile-based architecture before. And it's not obvious how you would use them in a case where you've got something more like an implicit flush, which there are many, and I'm not going to try and detail here. So Vulkan tries to to fix all of these problems. It's worth pointing out, like I said, these aren't just problems for tile-based architectures, they're problems for everyone's architectures, but they in some ways affect us more than others. So pipelines and state is, the whole idea of the state machine of OpenGL is completely overhauled for Vulkan. I mean, you've still got the same bits of state, but most of it is baked ahead of time and sort of considered static, and it's also tied to shader compilation. So rather than creating a shader with the GLSL that you may be familiar with and turning that into a compiled shader and then later setting some state completely dynamically, the pipeline object in Vulkan actually takes all of that state up front, or most of that state up front, and bakes it into one coherent thing, which is called a pipeline. And this means that you don't have to do any shader patching anymore. All that state's baked in, or at least an indication of what that state might be is baked in. And what the net effect of that is that whereas in OpenGL you may have had one shader and then you switch your state a lot, as far as the application is concerned, you now have in Vulkan a situation where you've got basically a ton of variants of your pipelines. Now, in most cases, it's not hideously bad. A lot of people really would only use one or two variants to any particular shader, and anyone who doesn't, it's not as bad as it might initially seem. We've got these constructs called pipeline caches and pipeline derivatives in the API. The idea being that if you do create two similar pipelines, as long as you use the same pipeline cache, or if they're a derivative of each other, you can save some work in the driver. So the pipeline cache, if it turns out a piece of state that differs between the two doesn't actually affect the shader code, then that pre-compiled shader, the compiled shader for the first one can be used again for the second one without having to do a second compilation. And then if you've got some state that it's quite expensive to switch, but you've got two pipelines that are derivatives of another pipeline, and between those they don't switch the expensive state, they only switch something that's quite cheap. It's possible to avoid switching that on the hardware by using the pipeline derivatives. I'm trying to think of a quick way to explain what derivatives actually are, because I just realized I haven't actually said what they are yet. The idea is you can have a base pipeline which says, this is my state, which I'm going to treat as a base. And then you can create derivatives from that one, which basically say, I'm going to be sharing a lot of state with my parent, and that allows the driver to build up a delta between the two, so it knows which bits of state. And then if you create other derivatives from the same parent, it knows the deltas between each of those derivatives and parent. And then when it comes to switching between derivatives, you just have to switch to the parent and then back to the new derivative, which can potentially be cheaper than switching the pipeline wholesale, depending on your architecture. So how that maps to our hardware. So for instance, in our hardware, blending is completely programmable. We have no fixed function hardware for blending. And that means that whenever you set a blend state in the API, some instructions are patched onto the end of the shader. Obviously, we employ various things to avoid that being particularly costly. So it is just a patch. And we also employ caching strategies to avoid having to create the same patch multiple times. The thing is, the shader is already optimized without the blending enabled. So when it comes time to bolting on these additional instructions, you do end up with a few small inefficiencies. Because if you could have that information ahead of time before compilation, you might be able to optimize some instructions out because you're either duplicating or you've got some pipelining in your architecture that allows you to put these things together. So having it ahead of time, like Vulkan does, means we can actually get a more optimal shader. And it may not seem like it's never going to be a huge volume of instructions for a particular shader. I mean, it might be like one instruction here and there, but it will add up. And overall, the different bits of things we might end up patching in certain shaders, it may lead to a big saving, and it may be the difference between a millisecond or two if you have a particularly complex scene. But it really does depend. It's very, very application dependent. And there's other bits of state that might fall into the same category. The frame buffer format for us as well, which is kind of tied to the blending, and the vertex layout. There's other bits as well that I'm not going to go into right now. And other architectures have very similar issues. I think nowadays a lot of architectures, whilst they do have fixed function blending for the basic modes, things like KHR Advanced Blend Equation introduced a whole ton of blending equations that really aren't going to be supported natively by many people. And I think, as far as I understand it, almost every architecture supports some form of programmable blending, although it may not be efficient. So back to synchronization. So I said before about how implicit synchronization means you end up having to flush a lot of things that you didn't necessarily need to flush, or you have to serialize work that shouldn't necessarily be serialized. So in Vulkan, you assume everything is completely there's no dependencies between anything, or at least very, very little. There's definitely dependencies between, I think as I mentioned last time, between setting some pipeline state and the draw call that comes after it. But individual draw calls only make very, very loose guarantees. Individual command buffers, I don't think there's any dependency between individual command buffers. And work on a queue, you have to explicitly say, I want this one to wait on this one if you really need it to. So it's very expressive. You've got a lot of choice of exactly when you need something. So you can say down to which shader stage you need something at. And that something can either be access to a resource. So if it needs any caches to be flushed, the implementation can do that. And if you need an operation to complete, then it knows to serialize those two operations, or at least the portions of those operations that need to be serialized. And the idea is that the implementation can create quite, well, not the implementation, the application can create quite optimal dependency chains. And you end up, if an app is quite savvy at this, you end up avoiding a lot of it flushing you might have had to do in OpenGL and improving performance perhaps quite a lot. So as I think I've mentioned already, PowerVR GPUs are tile-based deferred renderers. So that means there's 2 stages of rendering, as I mentioned. And one of the upshots of this is that you can run all, well, you have to run all the vertex work before you start rasterization, at least ideally. There are other things you can do, but that is the predominant way of working. And this means so if I give you an example, not a very specific example, but let's say you have rasterization working on an earlier, depending on an earlier task. Perhaps you're waiting for some other process or some other part of your system to be generating an image, but you're going to then texture some, maybe a video's being streamed in, and you're going to texture something in your scene with it. Now, your geometry processing does not necessarily depend on that. In fact, it would be quite unlikely if it did. So that can just go ahead and work, whereas your rasterization processing will probably depend on that task, and that might not be limited to one particular draw call, it might be limited to a whole set of draw calls. Now, if it's a whole set of draw calls, that doesn't make much difference to an OMR. It's going to have to pipeline everything. So it might wait until after the geometry stage, the vertex shading has been done for the first draw call, and then it will wait on that dependency. But really, that's not a huge saving, because that is just like one or maybe a few draw calls of geometry data that's been done. And there's strategies that I might be able to employ to do better than that. But from a sort of 5,000 mile out view, that's what it looks like. PowerVR GPUs, however, can keep working on that vertex data the whole time while the earlier task completes. So because we have this 2-stage rendering, we can just fully complete our geometry processing, which means we can keep our pipeline filled rather than waiting around for some other task to complete. And Vulkan really does allow that dependency to be called out very explicitly. So I mentioned immediate mode earlier with OpenGL, and Vulkan is very much not that. So submission in Vulkan is deferred, and I'm sure anyone who's been following this series is probably sick of me talking about command buffers by now, but there they are again. Work is organized into chunks. They are called command buffers, and basically allows implementations to batch work optimally. And that's sort of really your new unit of work. It's not really a draw call anymore. Your unit of work is a command buffer, which is a lot more meaty than what you would have had before. And then you also have the idea of queues, where you submit your command buffers to, and an implementation exposes exactly as many queues as they might have on their hardware. Well, not exactly, that there's obviously leeway, they can do what they want, but the idea is if you have one front end, you can expose one queue, and you can't submit work from multiple threads to the same queue unless you handle synchronization yourself, and that avoids having to do things like you would in OpenGL if you tried drawing from multiple threads, where you'd have to lock the queue down. So on PowerVR, for example, a command buffer effectively becomes a list of tasks. I suspect this is the same on many other implementations. For us in particular, it turns into tiling and rasterization tasks if it's draw calls, or it might turn into compute tasks, compute calls, etc., etc. And all the dependencies that are expressed inside the command buffer will have been baked into some form within that list of submission. When you actually take that command buffer to a queue and submit it, those tasks are kicked off. There will be some dependencies listed for those things. So all the rasterization for a particular set of draw calls is going to wait on all the tiling for that set of draw calls. And that's fine, because our hardware already supports that for obvious reasons. I say obvious if they're not obvious. It's just you can't start rasterizing until you have those tiles filled, basically. There's also explicit dependencies in the form of semaphores, which allow you to say, I want this command buffer to wait on this other command buffer, which is something the application completely controls. And another grouping that exists in the API is render passes. And these are specifically for rendering commands, at least at the moment. And the idea is that these map to what I said before, which is tile-based architectures really have a unit of work that's kind of like a render pass. which is what this is. So that was a deliberate choice of wording there. And the idea is certain operations that might cause flushes, things that would have been hidden in OpenGL, are just not permitted. So, for instance, if you ever wanted to express a dependency whereby you had some data written in a fragment shader in one draw call, and you wanted to access it in the vertex shader in the next draw call. Now, with an IMR, that gives you a small little stall while you wait for the first draw call to finish and the second one to start. It's not ideal, but it's only a tiny little hitch. Whereas with a tile-based architecture, that means running your entire rasterization pass for everything that's gone before and finishing it and then waiting for it and then starting again, as I vaguely mentioned earlier. And that is just not allowed in a render pass. And that's true of anything that would cause that sort of operation. Any sort of hidden mid-frame flush will be not allowed within a render pass. And you have to do it outside of a render pass. So it sort of gets an application developer thinking about what they're doing. There's also multiple subpasses in a single render pass. And each of these can communicate via pixel local image data, which allows you to write in one subpass, and then you can view those writes in the next. And I'll be talking about that in a minute, a bit more, because I think this may be where certain people, Andrew, if you're on the listening right now, you're interested in. So the other facet is that each subpass defines a LoadStore operation, and that defines how rendering begins and ends for each subpass. Again, going to go into some detail on that now. So how does that map to our hardware? Why the heck is this useful? So as I mentioned, this is useful just to batch chunks of draws at a time, because it means if we have the opportunity to batch these draws together with a guarantee that there will be no application flushing in the middle of it, then it allows us to keep the rasterization on chip. A flush does require a lot of work for us, so we really want to avoid that. And in particular, the actual act of the flush itself is expensive, but the real problem is the fact that when these happen, if you don't tell us, we don't know what to do with the tile data, which costs bandwidth. So the subpass, an individual subpass, gives you load and store operations, which is whether you can, I believe the load ops are you can clear, or you can ignore, or you can load. So you can load the data back onto your chip at the start of day. And the store operations, you can store it, you can resolve it to a multi-sampled texture, or you can again discard it. And this basically is a direct instruction to tilers to tell us, this is what I want to happen to this particular image attachment when you start and end rendering. And by making that an explicit choice, it really gets developers thinking about it. And it means that no one's just going to assume, well, the Vulkan API does not assume that these things will be written off chip if you don't tell them to. So it might still be written off chip on an IMR, although there's no guarantee of that. But it allows us to keep the flushes to places where we know what to do with the data. So the subpass, everything within the subpass it doesn't have to be, it's up to implementation, but the subpass is defined so that the whole thing can be kept on chip if you have such an architecture. We spent a lot of time looking at that. And that's just a subpass. So a render pass is a collection of subpasses, and they may be combined by the implementation. And this is possible because the only communication between subpasses is pixel local, as in ext shader pixel local storage. This is pixel local storage. It's in core. Basically, we can keep input attachments, which is the way in which you communicate between subpasses, completely on chip. So if anyone's not familiar with shader pixel local storage, it's basically exposing a set of registers on the GPU that you can communicate as you can between subpasses on a per pixel basis. So if you have a draw call affecting, I don't know, pixel 00, then second draw call comes along and looks at pixel 00, those two things can talk to each other, or rather the first one that executed can send data to the second one that executed. And that sounds kind of cool, and if you don't know what it's for, there's a couple of use cases. One of them is frame buffer fetch, is effectively using the same path, so that's programmable blending. Another really good use case is deferred shading. You can keep all of your G buffer completely on chip in these on chip registers. and then do your resolve pass without ever having going off chip, which avoids all, and I do mean all, of the bandwidth of the G buffer, which is the most expensive, well, probably the most expensive portion of deferred shading. And it really does enable doing deferred shading on a mobile device, which you couldn't really do without this. And the input attachments are the way we express this sort of communication. They don't even need to be allocated. So for pixel local storage, that was completely on chip. There was no off chip allocation done for it. And whereas for frame buffer fetch, it was just an image. We really wanted to keep that ability for Vulkan. So there's this idea of lazy allocation. So you don't have to use it, but in most cases, a driver that can do pixel local storage will not have to allocate a texture. And that's an explicit choice. There's an explicit bit that says, I don't know if this is going to be allocated or not, but if you don't want to allocate it, you don't have to. There's still a possibility that the driver may allocate it at some future point, but the option is there to not allocate it. And there is actually, I believe you're able to query how much memory has been used, so you can find out if you've actually consumed it or not. Oh, I missed the point. But yeah, so the upshot of all this is it basically expresses exactly what tile-based architectures like PowerVR GPUs do best. It allows us to keep as much data on chip as possible and saves an absolute ton of bandwidth in several cases. So to conclude, Vulkan really is designed to map to modern hardware, and I think we've done a good job of it. It does require a lot more information from an application. I mean, there is a lot of burden of proof, I suppose. No, maybe that's not the way to say it. That, yeah, you have to provide a lot of information, sometimes in slightly awkward places that you might not have expected to, especially if you've come from OpenGL. Even compared to DirectX 12, which doesn't have render passes, for instance, there's more information than you might expect. But this does mean it maps very well to PowerVR GPUs, and it should map equally well to other hardware. Render passes, particularly, are very useful for us and other tile-based architectures. It does mean that you may end up with some implementations ignoring some of the information you provide, but that's the sort of cost trade-off to allow everyone to map very well to the hardware. And the benefit there is that you get consistent performance across architectures. There's no hidden expensive operations. There's no need for driver heroics. It's trying to avoid these hidden expensive operations. You should know exactly what it's doing. As I mentioned last time, it's explicit API. But yeah, it's all about expressing the hardware and allowing you to get the best performance out of it. And that's not to say you will get the absolute 100% best performance, but it won't be a case of where you've got an OpenGL right now, where you have, you've got your path through your application or your engine for particularly optimized ones, where you choose a different path based on a GPU. You can still do that, and it's still viable to do so. People will still have extensions and features they exposed, but you should be able to get very good performance just following a single path. How long that holds remains to be seen, but at least for now, that is the case, and it's a great place to start from. Right, and that is it.